Hello and welcome to lecture 31 of analog integrated circuit design. In the previous class we analyzed the differential pair loaded by a current mirror active load in great detail. We saw how to analyze it conveniently, and that was by terminating it with a voltage source so that we see small impedances as loads, and then calculating the trans impedance or trans conductance of the differential pair. Okay. We have purely differential input, and this is loaded by a capacitor. We have really only one parasitic capacitance of consequence, because the tail node incrementally is not swinging, it has a tail node increment of 0. So, we have only the CD3, which consists of parasitic capacitances from all the transistors connected to that node. Okay. Now, under these conditions we saw that we could model the entire op amp with a trans admittance Ym, which was GM1 times 1 plus S CD3 by 2 GM3 divided by 1 plus S CD3 by GM3. Okay. And it also has an output resistance which is equal to 1 over GDS1 plus GDS3. Okay. So, this is the model corresponding to this op amp. So, it has a parasitic pole and 0 in addition to the pole at the origin or close to the origin due to the integrating capacitor. So, when we have such a frequency response, what will the magnitude and phase look like? This is the transfer function from the difference input Vd of the op amp to the output voltage Vo. Okay. Now, this is a relevant thing as we have used it in various loop gain calculations and stability considerations. Okay. So, the magnitude of the voltage gain will be GM1 by GDS1 plus GDS3 at DC or low frequencies. The dominant pole will be at GDS1 plus GDS3 divided by C. Now, this would be at the origin or 0 if GDS1 and GDS3 are 0. Okay. Then it follows an integrating type of behavior. So, it has a slope of minus 20 dB per decade. Let me assume that the parasitic pole and 0 occur beyond the unity gain frequency of the op amp. The unity gain frequency is given by GM1 by C. Okay. Please remember that with the parasitic pole and so on, the point where the magnitude plot crosses unity is not exactly GM1 by C, but if we assume that the parasitic effects happen beyond this, as we usually need for stability, the unity gain frequency can be assumed to be GM1 by C. Okay. there is another pole at GM3 by CD3. So, the slope changes to minus 40 dB per decade, and then at twice that frequency there will be a 0 and it changes back to minus 20. That is what the magnitude response looks like, and the phase response angle of V naught by Vd will start from small phase lags and go to minus 90 degrees, and here because of the pole it will dip down below minus 90, and because of the 0 it will come back up and then finally settle to minus 90. You can calculate the maximum phase lag that occurs because the 0 frequency is at twice the pole frequency. Okay. This is at minus pi by 2 and this is at minus pi. The phase never reaches minus pi really. Okay. Now, for stability it would be best if you have the parasitic pole and 0 beyond the unity gain frequency, okay, assuming that the op amp is in unity feedback. Otherwise, of course, you look at the unity loop gain frequency of whatever feedback loop that you have instead of the unity gain frequency. So, this is the frequency response of the single stage op amp. It is very simple and it is unconditionally stable because the phase lag never reaches minus 180 degrees. Okay. So, we have evaluated the gain of the op amp and the frequency response of the op amp, and from this of course, we can ascertain the stability. What we still have to do is to calculate other characteristics like the large signal limits of the op amp as well as non-ideal features like the noise and offset of the op amp. Okay. So, let us calculate the offset of the op amp. Now, the transistors M1 and M2 are supposed to be identical to each other, and M3 and M4 are supposed to be identical to each other, but there will be mismatch between them. Okay. So, we have to add appropriate sources to the circuit that represent the mismatch, find the output, and from there calculate the offset. The input referred offset is the useful representation of the offset in an op amp, that is the input voltage for which the output will be 0. Now, as before, while calculating the DC gain and so on, what we did was we did not calculate the output voltage directly, we calculated the output current going into a voltage source, multiplied that by whatever impedance is connected to the output to get the voltage. Similarly, here what we will do is calculate the output current going into a voltage source, because that is lot easier to do than calculating the output voltage. Okay. Now, because these offsets will be not necessarily symmetrically injected into the circuit analysis will become very complicated. So, usually while calculating the offsets and so on, we will assume that the GDS values are very small. Okay. Now, they will not affect the answers very much, but will give you will simplify the analysis sufficiently, so that we do not get bogged down with details. Okay. So, what I will also do to further simplify the calculations I demonstrate here is that I will assume that there is only a threshold voltage mismatch between MOS transistors. We very well know that there is threshold voltage as well as current factor mismatch. As an exercise, you please add the current factor mismatches. It is not very difficult. All you have to do is, if you have a pair of identical transistors, to one of them you add a current source in parallel that represents the mismatch. Okay. Now, if the inputs are identical and we have this the terminating voltage which is equal to VDD minus VSG3, the current here is 0. Now, because of mismatches between transistors, it will be non-zero. Okay. So, that means that if I have a transconductor with offset, if I apply 0 volts here, I will have some current there, which I will call the offset current. I want to represent this as an equivalent input voltage, and that will simply be equal to IOS divided by GM. Okay. Clearly, you see that if I apply 0 volts here, IOS by GM is applied to the transconductor and the output current will be IOS. Okay. So, as before, I will first calculate this current divided by the transconductance of this circuit to get the input referred offset. Okay. So, first of all, I will have two mismatches, one between M3 and M4 and one between M1 and M2. To represent the offset between M1 and M2, mismatch between M1 and M2, I can represent the threshold voltage mismatch as a voltage source in series with the gate. So, we already did this earlier in the exercise involving the current mirror. The threshold voltage mismatch, any change in threshold voltage can be represented as equivalently a change in the gate source voltage. Okay. So, the mismatch threshold voltage between M1 and M2 I will represent equivalently as a mismatch in the gate source voltage between M1 and M2. In other words, a series voltage source with the gate of M1. Let me call that delta VT 1 2. As with noise, the polarity of this is not important because we know that it is a random quantity. Finally, what we will calculate will be the standard deviation or the variance of this quantity. Now, what is the output current due to this voltage source? It is very easy. You can see that delta VT is simply the differential input voltage to the op amp. Okay. So, this is where we normally would apply the differential input VT. So, the output current is simply GM1 times delta VT 1 2, the transconductance times the delta VT 1 2. Now, this is a very common feature. Usually, you have the input signal applied to some transistors. Any offset due to the input transistors will directly affect the circuit. Okay. This will be more obvious when we calculate the input referred offset, but it is also clear from this example. The offset between M1 and M2 appears directly as an input signal to the circuit. We also have to calculate the effect of offset between M3 and M4. As with noise, the effect of each of these is very small. These are small signals and we simply add up the results. Okay. Now, for this analysis delta VT12 is 0 of course. So, we will not have this. Okay. Now, because these are at 0 and we assume that the transistors do not have any GDS and so on. So, the currents in M1 and M2 will also be 0. Okay. Because of that, the incremental voltage here will be 0. Again, you can confirm this with analysis if you wish. So, the gate source voltage of M4, the small signal gate source voltage of M4 will be delta VT34. So, the incremental current in M4 will be GM3, which is the same as GM4 times delta VT34, and that will go into the terminating voltage source. So, the total output current will be simply GM1 times delta VT12 minus GM3 times delta VT34. This minus sign is simply because of the way we have chosen the polarity, it is of no significance whatsoever. When we put in both mismatches, that is the current that we are going to have at the output. Okay. So, the offset current is GM1 times delta VT12 minus GM3 times delta VT34. As I explained before, we would like to represent this as an input referred offset voltage, and that is nothing but IOS divided by GM1. So, VOS will be delta VT12 minus GM3 by GM1 delta VT34. This is what I meant by the offset of the input differential pair appears directly as input offset. Now, this is in general true of offset and noise. You apply the input directly to some devices, and the offset or noise of the devices directly appears in the input referred offset or noise. Okay. Now, as usual, I am not interested in the exact value of offset for each device. What I really want is the mean square value of the offset or the standard deviation of the offset. Okay. Mean square value of the offset is nothing but, let me represent it as sigma VOS square, sigma VT12 square plus the ratio GM3 by GM1 square times sigma VT34 square. Okay. And sigma VOS is nothing but the square root of this whole thing. Okay. The effect of M1 and M2 you simply cannot avoid, and effect of M3 and M4, the offset between them is multiplied by the ratio GM3 by GM1. Now, if you have a small GM3 and a large GM1, it will be divided by a large number and will be negligible. Okay. Now, the way to think about this is that the input transistors M1 and M2 convert the input voltage to a current. Now, the load transistors M3 and M4 will add an offset current of their own, which is proportional to GM3 times delta VT34. Okay. When referred to the input, that will get divided by GM1. So, if you make the offset current added by the load devices small and the transconductance of the input devices large, the effective offset due to the load at the input will be small. So, there is some room to play as far as the offset of the load is concerned. As far as the offset of the input is concerned, there is nothing you can do, it appears directly at the input. The only way to reduce that is to increase the area of the devices. Okay. So, by making the input devices bigger and bigger, you can reduce the offset, and if you want to make the overall offset small, you have to make both the input devices large and the load devices large. Okay. And this can be further calculated from the process data. AVT square by W1 L1. By the way, this is the AVT of the NMOS transistors, which could be different from the AVT of the PMOS transistors. So, with this you can calculate the standard deviation or variance of the input offset. So, what it really means is, let us say this sigma VOS comes out to be 2 millivolts. So, if you make a million op amps like this and then measure all their offsets, 99% of them will have an offset less than 3 millivolts, that is plus minus 3 millivolts. Okay. So, from this and the kind of guarantee that you want that the offset be less than a certain value, you can figure out how much sigma VOS you have to design for, and whether the op amp sizes that you have chosen, the transistor sizes that you have chosen are adequate or not. Now, the next thing to be calculated is the noise. So, we will again finally calculate the input referred noise of the circuit. Okay. As before, we will calculate the output current going into a terminating source V term. Okay. As with offset, we will calculate the output current and from that calculate the input referred noise, and we know that the equivalent input referred noise will be the output noise current divided by the GM. Okay. In earlier examples we were calculating the output noise voltage, but it is exactly the same here. We calculate the current instead and divide it by GM1 to get the input referred noise voltage. As we mentioned earlier, the input referred noise voltage is an equivalent representation. It is not a noise voltage that appears anywhere in the circuit, but it is something that will represent the effect of all noise sources in the circuit. Now, as with offset calculations, we will by and large ignore GDS in the calculations, because that will only lead to more cumbersome expressions without any extra insight, and usually it also does not quantitatively affect the results very much. Okay. So, what should we do when calculating the noise? We have to add noise to each transistor, every noise generating device. In this case, we have only transistors. Okay. And we have to find out the transfer function from every noise source to the output, and finally add up all of them in an uncorrelated way to get the output noise spectral density, divided that by GM1 square to get the input referred noise spectral density. I also have to add the current source transistors here, M0 and the current mirror. Okay. Let us assume that this is biased from a current mirror. So, first in quiescent condition, of course, I out is 0, and let me add a current IN0 that is due to M0. Okay. Now, if I have a current IN0 due to M0, there will be an incremental current in both M1 and M2. Okay. There will be no incremental current in M0 because its output conductance is 0. There will be an incremental current in both M1 and M2. And how much will that be? We know that the impedance looking up here is 1 over GM1, because the drain is loaded by a relatively low resistance. The impedance looking up here is also 1 over GM1, because its drain is loaded by a short circuit, which is also a small resistance. So, this current divides equally, and we have IN0 by 2 and IN0 by 2. Okay. Now, IN0 by 2 in M1 goes through M3 and gets mirrored in M4. So, we have IN0 by 2 and IN0 by 2 over there. So, what is I out? We have IN0 by 2 here and IN0 by 2 there. So, I out due to IN0, that is the noise current in M0, is 0. Okay. Now, this is general result. If you inject something into the common mode node or the tail node of an op amp, now in the difference output the effect will be 0, okay, because it will get symmetrically divided into M1 and M2 and mirrored in M3 and M4, and the net effect will be 0. Okay. So, the noise of the current source transistor does not appear in the output of the op amp. Let me copy this over. Let me now calculate the noise due to M3 and M4. Okay. This represents the noise due to M4, and in small signal this is grounded, okay, and this point is also at 0 because of this constant voltage source. So, all of this current source simply goes into I out. Okay. So, the effect of noise current due to M4, let me tabulate all the transistors here, will be that all of IN4 appears at I out. With the polarity I have chosen, it happens to be minus IN4. If I look at the noise current due to Mn3, what happens? The impedance here is infinite. We will assume the GDS of these transistors is 0. So, this IN3 simply is drawn out of this diode connected transistor M3, and we know that M3 and M4 form a current mirror. So, the same current appears here as well, and it has to go into the terminating voltage source because that has 0 impedance. Okay. So, IN3 also appears directly at the output. Okay. We then have to calculate the effect of noise currents in M1 and M2. Let us say I consider the noise current in M1. Okay. Now, the earlier noise sources had one of their terminals grounded. Now, this is connected between two nodes, the drain and source of M1. The analysis can be a little more complicated. It is not very difficult, but it can be a little more cumbersome, but there is a very neat trick that makes it very easy. In any circuit, let us say I have a current source between A and B, I can replace that with a series combination of two current sources of exactly the same value. So, let me call this Ix, okay. This will be Ix and that will also be Ix. Okay. Clearly, KCL is satisfied here and also nothing has changed at nodes A and B. So, this is fine. Now, if I take this node and connect it to any other node, again it will not affect the circuit because these two currents are by definition identical and the current flowing here will be 0. So, I could connect it to any other node without affecting KCL at that node and consequently without affecting the circuit. Okay. Now, this is a particularly convenient thing when we have to do analysis with floating current sources, that is current sources connected between two nodes, neither of which is ground. In many cases it will simplify things if we replace it as a series combination of the two current sources and connect the middle node to ground. Okay. So, that is what we are going to do here. Most important thing is the two current sources should be identical, and in this case they are noise sources, but the noises are identical. Okay. Now, normally you are used to calculating noise from different sources and assuming they are uncorrelated. In this case they are perfectly correlated, okay, because we are simply replicating the current, and we will connect the middle to ground and we will analyze the two separately. Now, we do not have to do further analysis because this IN1 is like the previous analysis we did with noise current source of M3, and the lower IN1 is like the analysis we did with the noise current of M0. Okay. So, let me put them in different colors just for clarity. IN1. What will happen due to the upper IN1? All of it will flow into M3 and get mirrored into M4. Okay. And what will happen due to the lower IN1? It will split into IN1 by 2 and IN1 by 2, exactly as we discussed for the noise from M0, and whatever goes through M1 also goes through M3 and gets mirrored. Okay. So, we have a net current of IN1 by 2 in M4 and IN1 by 2 in M2. So, the total current flowing out will be equal to IN1. Okay. So, it turns out that all of the noise current of M1 appears at the output. It takes some complicated path, half of it goes through M3 and M4 and half of it through M2, but it will come out entirely. Okay. Now, in a very similar way, the noise of M2 can be analyzed, and it turns out that exactly the same thing happens, and all of the noise of M2 will also appear at the output. So, you can do the analysis just as practice of this kind of analysis. Okay. All of IN1 will appear there, and if we do this with polarity downwards, this will turn out to be IN minus IN2. So, the output current will be the sum of noise of all these devices, and the tail device does not contribute anything. Okay. It will contribute equal currents to the two halves and they get cancelled out. Let me rewrite it here. So, the noise spectral density, which is what I am interested in, is the sum of the spectral densities, because these terms are uncorrelated from each other. Okay, which is IN1 and IN2 are proportional to GM1, IN3 and IN4 are proportional to GM3. Okay. So, this is 16 by 3 kT GM1 plus GM3, and the input referred noise voltage source is nothing but SI out divided by GM1 square. Okay. Because an output current can be represented by an equivalent input voltage by dividing I out by GM1. So, this is equal to 16 by 3 kT 1 over GM1 plus GM3 by GM1 square, which can be rewritten as 16 by 3 kT by GM1 1 plus GM3 by GM1. Okay. So, that is the expression for the input voltage noise spectral density. Now, we have ignored the frequency dependence and so on, that is not so important with noise, and also that it will lead to messy and cumbersome expressions. If you do want to calculate the frequency dependence of this input and output noise spectral densities, you go to a simulator, but this expression is good enough for us for a wide variety of calculations to estimate the noise. Okay. Now, one thing to observe here is that the first part of this expression is 16 by 3 kT by Gm. Now, we know that if we refer the noise of the MOSFET to its input, it will be 8 by 3 kT divided by Gm. That is, if we represent the noise as a noise in VGS instead of ID, it will be 8/3 kT divided by Gm, and we have two transistors which have uncorrelated noise. So, their spectral densities add up and we end up having 16 by 3 kT divided by Gm1. Okay. So, as I have mentioned many times, the noise from the input transistors contribute directly to the input referred noise. Now, the second part of this is the contribution of the load transistors. Just as in offset, you see that you have the expression Gm3 by Gm1 appearing there. By making the transconductance of the load much smaller than the transconductance of the input transistors, we can reduce the noise contribution of the load. Okay. But the noise contribution of the input transistors does appear directly, and the only way to reduce that is to increase Gm3, and we know that increasing Gm3 will contribute to increased power dissipation, because we have to have more current in the transistor. Okay. So, we have calculated in detail the small signal parameters of the op amp, the DC and AC gains and frequency response and so on, and also the offset and noise. What is left is to calculate the large signal limits. I will show the transistor here because that is relevant to this analysis. Let me call it M0, M1, M2, M3, M4. Now, we have several things going on here. We have the input V bias and a difference voltage Vd and the output. Okay. Now, when the op amp is operating in a negative feedback circuit, the difference voltage Vd is expected to be very small. Okay. So, that is the basic idea behind using an op amp in the first place. So, what we will do is assume that the Vd is usually so small that it will not drive any transistor into the triode region. So, it will not directly affect the swing limit. What will happen is that it will affect the output and the output voltage will be limited. Okay. It is not the swing of the input voltage Vd that will push any transistor into triode region, but it is the output swing that may push some transistors into triode region. So, that is one thing. And secondly, this V bias, so far we have not defined it. In an op amp itself, we can have different values of V bias. We will come to it when we talk about single supply and dual supply operation of op amps, but so far we have simply assumed that V bias is such that all transistors are in saturation. So, we have to find out the limits of V bias for which that is indeed the case, that is the transistors are in saturation. Okay. So, what we have to do is to find the limits on V out and V bias. We will assume that Vd is 0. Okay. So, I will remove Vd from this picture. Now, what happens if V out increases? If V out goes on increasing, the transistor M4 will get squeezed, that is its VDS will reduce and that can go into the triode region. And when will that happen? Let us assume a supply voltage of VDD. So, V out has to be at most VDD minus VD sat of M4, okay, which is the same as VD sat of M3. Now, we will assume that these saturation voltages are calculated at the quiescent operating point. By the way, this definition of VD sat I am assuming you are familiar with. VD sat is nothing but square root 2 ID by mu Cox W by L of the respective transistors. This is the gate overdrive or the VDS that is required for saturation. Okay. So, VD sat 4 and we will calculate it at a current of I naught by 2, and in this particular case this will be 2 times I naught by 2, and what we have here is W3 by L3, that is the same as W4 by L4. Okay. Now, on the other hand, what happens if V out starts decreasing? As V out decreases, you can see that the gate of M2 is at this voltage V bias. Okay. So, as V out reduces, M2 will go further and further into the triode region. Okay. The output voltage V out can go below V bias, but not by more than 1 Vt. So, I call this as Vt1, which is the threshold voltage of the NMOS transistor, and Vt2 of course is the same as Vt1. Okay. So, these are the limits on V out. We have to also find the limits on V bias. Now, earlier we argued that by symmetry this output voltage will be exactly equal to the drain voltage here when no current is flowing out. Okay. So, that is the case that we will assume. We will assume that no current is flowing out of here. In reality, of course, we will have our capacitor connected here and then some feedback network and so on. For now, we will assume that no current is flowing over there. And that is true independently of the value of V bias. Okay. The current here will be I naught and the current there will be I naught by 2 and I naught by 2. So, what happens is as V bias changes, the current in M3 and M4 will be exactly the same and the voltage here and here will not change. We will assume that the GDS of these transistors are very small. What will change is this voltage, that voltage will be V bias minus VGS of M1 or M2, I will write VGS1 here. So, the tail node simply follows V bias. Okay. So, as V bias comes to very small values, the transistor M0 goes into triode region. Okay. Its VDS becomes smaller than its VGS minus VT. So, it goes into triode region and that will limit the lower value of V bias. So, V bias has to be greater than 1 plus VD sat 0 and VGS1 itself can be written as the threshold voltage VT1 plus VD sat 1. Okay. So, what is important here are the ranges. So, VT1 is a threshold voltage plus 2 overdrive voltages above ground, that is the lower limit on V bias. Now, what happens if V bias goes on increasing? As we said, the drain of M1 and M2 do not change. Okay. They will be at a fixed value equal to VDD minus VGS of M3 at a current of I naught by 2. Okay. These voltages will be VDD minus VGS3 at a current of I naught by 2, the same holds here as well. So, the drain is at a fixed voltage, the gate voltage is increasing for M1 and M2. So, M1 and M2 will go into triode region if the gate voltage increases beyond the drain voltage by more than 1 VT. Okay. So, V bias has to be less than the drain voltage VDD minus VGS3, which I will write as VDD minus VT3 minus VD sat 3 plus VT1. Okay. So, these are the limits on V bias. So, let me rewrite them here. The output range is given by that and the input bias range or the input common mode range. V bias is nothing but the average value of the inputs, right. So, input common mode range is given by that on the upper side and on the lower side VD sat 1 at a current of I naught by 2 and VD sat 0 of transistor M0 at a current of I naught. Okay. So, these are the ranges. Now, of course, this will give you some numbers if you calculate, but what you should particularly observe is that the output voltage can go fairly close to VDD. Okay. The normal range of saturation voltages are maybe 100 to 200 millivolts, especially in modern low voltage technologies. So, it can go close to VDD, of course, not exactly equal to VDD, but within 100 or 200 millivolts of VDD. Okay. So, on the upper side the limit is quite good, but on the lower side it depends on V bias. Okay. So, if V bias happens to be half of the supply voltage, so this can go only a little bit below half of the supply voltage. Okay. So, this is good and the other one is not so good. And as far as the input common mode range is concerned, again on the upper side the limit is fairly close to VDD. Okay. If we assume that the threshold voltage of NMOS and PMOS transistors is the same, then VT3 is approximately equal to VT1 and that will cancel out. You see that the upper limit is within one saturation voltage of VDD, that is VDD minus VD sat 3. Okay. So, again on the upper side the input range is good, but on the lower side it is limited to quite a bit above the rail, quite a bit above the lower supply rail, which is 0 volts. Okay. So, it is equal to the threshold voltage plus the sum of VD sat 1 and VD sat 0. Okay. What I mean is that we have 0 and VDD, which represent the lower and upper rails. The output voltage can go fairly close to VDD, I will represent it by this line. And on the lower side it is limited by V bias. Okay. It has to be within this region, that is the range for V out, and V bias itself can go fairly close to VDD, that is VDD minus VT3 plus VT1 minus VD sat 3. It is similar to the upper limit on V out, and on the lower side it is limited by VT1 plus VD sat 1 plus VD sat 3. So, it is very obvious from the expressions that this gap is lot more than that gap. Okay. So, that is the range for V bias. So, with the particular topology that we have chosen, limits are closer to VDD than to ground. Now, this is a property, this is a feature of having chosen NMOS differential pair input transistors and a PMOS load. If we chose PMOS input transistors and an NMOS load, the situation would be reversed. You could go lot closer to the lower rail, and you could only go a lot farther from the upper rail. Okay. So, these are also some considerations which will enable you to choose between NMOS and PMOS transistors. Okay. If you want an input common mode range very close to the lower rail, you have to use PMOS transistors. If you want input common mode range close to the upper rail, you have to use NMOS transistors. Okay. So, these are the large signal limits of the op amp. Now, we will elaborate a little further on this when we discuss single and dual supply operations of the op amp in the next class. Okay. Thank you.